Okay, today I want to talk about orbital mechanics, the study of planetary motion using Newton's laws, getting away from the notion of the laws of the heavens are different from the laws of the earth. It's going to get fairly intense mathematically, so I'm going to split it up over 2 days. I'll do the lecture today, I'll give you the worksheet. You'll have today and tomorrow to work on the worksheet. You can ask me questions. You should ask me questions because some of this isn't the most straightforward in the world. So we left off here where we figured out Kepler's third law was going to be t squared is proportional to r cubed, period and radius really to each other of orbit. On the PowerPoint, when they go to the next slide, they show a modified form of Kepler's law here. I want to show you where that comes from and why. So that means we're going to go to my whiteboard here and do some math. Remember, again, Kepler's law, put it over in the corner here. T squared is proportional to, so is equal to a constant times radius of orbit cubed. And back in the good old days, that was just a law of the heavens and had no relationship to the laws of the earth or anything of the nature. Newton's genius was to realize that it's all one set of laws. And using his law of gravity, he could actually, which by the way was derived using earthly motion, the fall of an apple and that kind of thing, and use it to derive Kepler's law. So let's start with F equals G M over R squared. The force of gravity between any two masses is equal to the constant times the first mass times the second mass over the distance squared between them. That radius is from center to center of the planets, stars, whatever. In this case, it's going to be the big M, capital M, is the mass of the sun, and the lowercase m is the mass of the planet orbiting the sun. However, we'll see the laws we derive here are going to apply to anything. So big M in general is going to be whatever you're orbiting. Little m is the body in orbit. So if big M is Jupiter, little m could be like Europa, one of Jupiter's moons. So first thing is, if this is a planet orbiting the sun, again, capital M is the sun, lowercase m is the planet orbiting it, this force that of gravity is holding it in its orbit. And so that is a centripetal force. That's the key to getting all this. The force of gravity holding a planet in its roughly circular orbit is a centripetal force. Now, we're going to assume circular orbits here in our discussion. If you go through the calculations with elliptical orbits, it still works out, although obviously it's more complex. Now, since that's the centripetal force, we can replace it with what we learned centripetal force equals at the beginning of the chapter, and that is mv squared over r. Still equals g m over r squared. Now, which m is this? Well, that's the mass of the thing spinning in circular motion, so the mass of the planet orbiting the sun. Notice the mass of the planet cancels out of the equation. Doesn't matter how heavy the planet is, only matters what sun you're orbiting, the mass of our sun. So, notice also this radius and one of those radius values will cancel out, giving us, and I'm going to rearrange a little bit here, actually I don't need to rearrange, v squared equals gm over r, or v equals, well, I'll write it down like that, v squared equals gm over r. Now, we're going to continue on with this derivation, but if you do square root both sides, you get v equals the square root of the terrible equal sign, equals the square root of gm over r. The whole thing's under the radical there. That's a useful equation for any planet or any body in orbit of any other body, really. We now have an expression for the orbital velocity. So how fast is the Earth orbiting around the sun? What's its orbital velocity? There you go. V equals square root of g times mass of the sun over radius from the sun, which is 1 AU. Translate that into meters and you're all set. Plug it in, square root. You got our radius. You got our velocity. Once you have the velocity, of course, you can get omega or period or whatever else you want. Now, so that's a useful equation, and you're going to use that in the problems I give you. By the way, you're also going to use all the circular motion stuff for omega and period and frequency and all the other stuff too. You'll also use Kepler's law. You'll also use the force of gravity and the acceleration of gravity. So there's a lot here mathematically to deal with. Now, let's come back to our v squared equals gm over r. Remember that, again, I'll come over here and write it. For an object in circular motion, velocity is the distance over the time. The distance around a circle is the circumference, 2 pi r, over the time for once around the circumference is the period t. So we could take that and plug it in for velocity there. And what we'll get is, well, it's squared, so 4 pi squared over, r squared over t squared equals gm over r. Little separator there. So that's just plugging in, and now you could rearrange algebraically there. Notice bringing this r up, you get a radius squared. Bringing that t up, you get a radius cube. Bringing that t up, you get t squared times gm. So basically just cross multiply and then simplify. I'm going to cut right to the chase here, but you guys can actually go through and do the algebra yourself. You get t squared equals 4 pi squared over gm times r cubed. Now, that's the result I was looking for here. Doesn't look like much, but take a look at it. T squared equals this mess, which is just a constant for our solar system, times r cubed. In other words, we get t squared equals k times r cubed. And that's exactly Kepler's law. Better than Kepler's original law because k was just an empirical constant there, just it is what it is because the heavens are what they are. Here Newton says, well, no, it is what it is because you plug in 4 pi squared g, all numeric constants for our universe, and the mass of our sun. So if I orbit a different sun, I'd get a different k. If I have a moon orbiting Jupiter, I plug in the mass of Jupiter instead of the sun, I'd get a different k. So it explains why you have different k values for different primary bodies of orbit. But again, notice Newton found Kepler's law, t squared equals, well, this ugly constant times r cubed. And he derived it from laws of Earth. And this, once and for all, showed that the heavens were no different. The Earth and the heavens work exactly the same, follow the exact same laws, and there was no longer distinction between the two. Now, this equation is going to be very useful for you in calculating orbital parameters and masses of primaries. For example, if I give you, the mass of Saturn and the radius of some moon orbiting Saturn, you could plug in, calculate its period. I give you the period, you can find the radius. But even better, if you don't know the mass of a planet, and remember back in the day they didn't just know the mass of Saturn, right? So you can figure it out. You could take your favorite moon of Saturn, plug in its orbital period, plug in the radius of the moon from Saturn, and rearrange and solve for the mass, and now you know the mass of Saturn. This is how we know the masses of all the other planets and stars out there. We get it from calculating based on their moon's orbits. Among the last planets that we really truly knew their masses, other than guesses or estimates, were Mercury and Venus. We didn't really know those for sure until we had space probes orbiting because they have no moons. So you could base your understanding of their masses by knowing they're rocky planets and probably have a density similar to Earth and calculate from there. But without moons, you can't do this calculation. Mars, Jupiter, Saturn, all those others, we knew their masses to very high precision even before we sent space probes there because we could calculate it based on the radius and periods of their moons. Okay, so again, tonight you'll have a worksheet on this where you'll use all the equations we've been dealing with, from circular motion to G equals GM over R squared, this new velocity equation, and this new Kepler's law version of the equation. And you're going to calculate all kinds of things for moons, planets, orbiting, whatever. And again, that worksheet will be due at the end of the day, Tuesday. It's Monday and Tuesday's assignment because it'll keep you busy. All right, again, ask me questions. That's what I'm here for. And we are done.